Hello and welcome to my channel. Today we will talk about implicit differentiation. We will solve a few examples, but this is just an application of the chain rule. So let's consider this case where y is going to be a function of x and u will be a function of y. If I want to take the derivative of u with respect to x, the chain rule tells me that I have to take the derivative of u with respect to y and then the derivative of y with respect to x. What we will be doing with implicit differentiation is we will have a function of y here, and we're going to leave the function, or the derivative rather, dy by dx indicated. So let me give you a quick example. Let's say we have x squared plus y squared equals 1, and we want to compute the derivative of y with respect to x. What we can do is take the derivative with respect to x on both sides. So derivative with respect to x on both sides. What I get on left-hand side, I can take the derivative term by term, and add them. That's the linearity of the derivative. So I can take the derivative of the first. That's just going to be 2x by the power rule. Now here, this would be the function I'm referring to u of y. So what I have to do, according to the chain rule up here, is take the derivative of y squared with respect to y. That would just be 2 times y. That's the power rule. So that's going to be your du by dy. And now chain rule tells me I have to still pay with dy dx. And then that would be equal to the derivative of 1 with respect to x, which is 0. Now, what did we obtain? We obtained a function, or an equation rather, 2x plus 2y dy dx equals 0. That is a linear equation with respect to, if you consider dy dx as your variable. So that means I can solve it by the traditional means, which would mean, in this case, I subtract 2x on both sides. And then I obtain 2y dy by dx equals negative 2x. Then all I have to do is divide both sides by 2y to obtain dy by dx is negative 2x over 2y. And simplifying that rational function, we can write it as dy dx is going to be negative x over y by canceling those 2's there. And that would give me the derivative at any point. And by the way, the equation I chose was the unit circle, so this would be the derivative at any point on the unit circle. So in the next few minutes, we're going to be working on a few examples of implicit differentiation. So hang on, and if you have any questions, let me know in the comments below. Alright, so now we're going to look at implicit differentiation. So here the point is we're going to take the derivative with respect to x on both sides. So derivative of the constant is always going to be 0. This is a common mistake, and just people write 6 instead of 0, or even 1. No, derivative of constant will be 0. That one should be okay. Now derivative of this. Now notice you have a product, 3x to the 5th times y squared. So we're going to address them with a product rule. So derivative of the first times the second. And then we're going to have plus, copy the first, times derivative of the second. And then minus, and I'm going to open a parenthesis because I want this negative to remind myself that I'm going to apply it to each term. But whenever I write my product rule, I may forget that I have a minus, and then I can change the sign of the second term, and that would ruin my problem. So let's not do that. So We have a product, so the first term we can consider it to be 2x cubed, and the second y cubed. So we're going to have derivative of the first times the second, plus, because I put my parentheses out here, I can write it just as plus. I can continue to do my regular product rule. Copy the first times the derivative of the second. Okay, so now we have to compute those derivatives. They're just power rules, so not that big of a deal. 5 times 3, 15. X to the power of 5 minus 1, so 4. Y squared. Now I get 3x to the fifth. Now this derivative is the one that you have to be a little bit careful with, because I'm taking the derivative with respect to x, and I have a term that is a y, so I need to use chain rule for it. So I get the derivative of this with respect to y is going to be 2y, but I have to pay to convert it into the derivative with respect to y, to x with a dy by dx. Because this right here would have been the derivative of y squared with respect to y, not with respect to x, which is what I needed. So that's the one where you have to be careful. In the book, they'll write y prime. I guess it's weird. I normally don't like writing extra, but this time I write dy by dx. Usually because when I'm solving for the equation, I like seeing that dy by dx rather than y prime, because I may miss a y prime. So now minus, let's distribute that out. And I get a quotient rule here. So 3 times 2, 6. X to the power of 3 minus 1, 2. And copy my y cubed. And again, this one is, not plus, minus, negative times positive. So you see, that was the risk I was trying to avert, and all of a sudden I'm doing it again. So then the derivative of this one, 3y squared. And remember, that would have been the derivative of this with respect to y. Change it into x by paying the price with dy dx. And so now I have this expression. Let's just multiply things out. And we get 15x to the fourth y squared. The 2 times 3 is going to be plus 6x to the fifth y dy dx. And then minus 6x squared y cubed minus, now 2 times 3, 6, x cubed y squared dy by dx. And now the thing you gotta be very mindful of is to locate your dy by dx. And this is why I like writing dy by dx rather than y prime, because they're easier to locate. So you're going to add and subtract things in order to keep dy by dx on one side. Usually we like it on the left, but today we're going to leave it on the right because they're already on the right. So what I'm going to do is I'm going to send this guy to the other side by adding it, not this guy, this guy. And I'm going to send this guy to the other side by subtracting. I'm not going to have room to put them both, but the net effect will be the same. We can just get 6x squared y cubed minus, I'm going to subtract this guy. I didn't write it out, but I think everybody's okay with that. And then we copy the other guys. The whole point of doing this, and by the way, I was not faithful to my simplify before, because here you had a common factor y squared and x cubed that you could have factored out. Oh, never mind. Take it back. You could have done that, but then your derivative would have... Never mind. Ignore me right now. So we'll go ahead, I guess. We'll go ahead and factor that dy by dx. So right here. And so copy this. I thought we could simplify it more, but I guess this is as good as it gets. So let's factor that out. 6x to the fifth. We will simplify at the very end, but it's not going to be as nice as I thought. So sad. dy by dx. And now we divide both sides by the term that is multiplying the dy by dx. Put it on the left just so it looks pretty. So we're going to have the numerator will be what we have here on left hand side. And the denominator will be the term that is multiplying our dy by dx just by dividing both sides by it. And now we can go ahead and simplify our expression by pulling out a common factor y, a common factor x squared, and canceling them out. But we'll leave it at that, like we have it here. All right, let me stop right here. So this one is a little bit more complicated because it has a chain rule within the implicit differentiation. So let's take a look. And what you want to do when you have these kinds of problems, you kind of want to work from the outside in. It's like with chain rules. I kind of think about it like an onion. You're working your way from the most outermost peel further in and in and in, and there's several layers. That's kind of how I think about it. So let's take the derivative on both sides with respect to x. So firstly, the left hand side is going to be 0. That one is the easy one. Again, but some people make the mistake because they're so caught up on what's coming after that they just write -3 and the problem gets ruined there. So derivative of this is 0. Derivative of the cosine is going to be negative sine. And you see, you're going to have a chain rule. Why do you have a chain rule? Well, because you have the cosine, sorry, but it's not cosine of x, it's cosine of something else. So you have to then, whenever you don't have just the cosine, but cosine of something else, you have to do your chain rule. So you're going to go ahead and copy the inside. And by the way, you work each step in a different line. Don't try to do it all at once. That's a very, very common mistake when it comes to chain rule or these kinds of problems where there's several functions composed with one another. People want to do it and get it all in one line. There's no need. I mean, that's a recipe for coming up with mistakes or finding or making as many mistakes as possible. Just do one at a time. So your outermost layer is the cosine. Take that derivative first. Deal with what comes after later. Just leave that derivative indicated. Yeah, but there's a y, there's a tangent. What am I going to do? Don't worry about it. For this line, you're just worried about that cosine. That's all you're worried about right now. The next will come. You work on it the next line, so don't let it overwhelm you. What happens is if you see it all as a whole unit, it looks very difficult. But when you start breaking it down and just working one step at a time, it's not too bad, you'll see. Now I take the derivative of y with respect to x, so that one is just dy dx. That one is just that. And so, or if you want it, you take the derivative with respect to y is a 1 times dy dx. Same deal, same end result. Now I get the derivative of this tangent. So minus derivative of the tangent is going to be secant squared. Evaluated at the inside, you see it's not just an x, it's a 3x. So you're going to have to do a chain rule. So secant squared is the derivative of the tangent. Evaluated at the inside, 3x times the derivative of the inside. So you see, again, I'm doing each layer, I'm doing one row for the next layer, which was this outside layer, which happens to be the tangent. Now I'm going to deal with the innermost layer, which is going to be the 3x at the very, very end. So I take it one step at a time, and that makes it a lot more manageable. It's like eating an elephant, right? A little piece at a time. I wonder what elephant meat tastes like. Never mind. So we get dy by dx. And then we have the derivative of 3x is just going to be 3. Secant squared of 3x. Now this function, it looks very, very, very daunting. But you see this function is equal to 0. So you can think about dividing both sides by negative sine of y minus tangent. So this term would quote-unquote cancel. The reality is we're thinking there's two numbers multiplied times each other, and they can only be 0. The product can only be 0 if one of them is 0. We don't care when this term is 0. We only care when this term is 0. So that is going to give us our equation that will give us the derivative dy dx minus 3 secant squared of 3x. And then we add 3 secant squared of 3x on both sides, and we get that the derivative of that function is 3 secant squared of 3x. And that's that.